Welcome back to The Explainer. Today, we're getting right to the bottom of how Ethernet standards actually transmit data. You know, we tap our screens, click our links, and just expect this instant digital magic to happen. But beneath all of that is this fascinating, highly orchestrated world of electrical pulses, optical lasers, and some very strict invisible rules.
It's kind of crazy to think about, isn't it? What's actually happening the exact second you plug a cable into a port? In literally a matter of milliseconds, an unbelievable sequence of events takes off to let your data cross rooms, oceans, and pop up on your screen. We're going to explore the exact physical mechanisms, the pin layouts, and the microscopic light waves making it all possible.
To figure this out, here's our agenda. First, the IEEE Ethernet standards. Second, transmitting data over copper. Third, sending data with light. And finally, the auto negotiation handshake. Let's jump right in.
Starting with Section 1, the IEEE Ethernet standards, or how we define the invisible rules of the Internet.
Think about it like this. Every single time your computer talks to a router, it's following a strict set of rules. And to really appreciate this, you gotta imagine the absolute chaos of early networking before 1983. Back then, a computer made by one brand might have literally zero way to talk to a switch made by another brand. It was a mess. But that all changed when the Institute of Electrical and Electronics Engineers, the IEEE, stepped in and defined the 802.3 Ethernet standard. It was a total game changer. By setting a universal language, they built the foundation for the internet we know today.
Now, before we get into speeds, we've got to bust a major myth. Network speed is measured in bits per second, like kilobits, megabits, and gigabits. And in networking, 1 kilobit is exactly 1,000 bits. This is completely different from the bytes used for your hard drive storage. Conflating these two is exactly why so many people think their internet is running slower than advertised. When you pay for a 100 megabit connection, no way are you downloading a 100 megabyte file in 1 second. You're getting 100 megabits, which is only about 12.5 megabytes. Keeping that straight is absolutely essential.
So looking at how copper Ethernet has evolved, it's pretty wild. We've gone from the old 10 base T standard at just 10 megabits per second all the way up to a massive 10 gigabits per second with 10 G base T. That's a 1,000-fold increase in the data being pushed through a wire. But there's a catch. Every single one of these standards hits a literal brick wall at exactly 100 meters. Push an electrical signal past 100 meters on standard copper, and the data just degrades into unreadable noise.
Which perfectly brings us to Section 2, transmitting data over copper, or how we actually move those bits across the room. The go-to method for staying within that 100-meter limit is UTP, which stands for Unshielded Twisted Pair Cabling. And fun fact, those internal wires aren't twisted just to keep things neat. It's pure physics at work. Twisting them creates a magnetic shield that naturally cancels out outside interference. Without that twist, even a nearby power cable would corrupt your data instantly. And at the end of that cable is the classic, clear plastic 8-pin connector you've definitely seen before, officially known as an RJ45. Now, here's where it gets really interesting. Inside that little RJ45 connector, not all 8 pins are doing the same job. Routers and PCs, they transmit their data, or TX, on pins 1 and 2, and they listen, RX, on pins 3 and 6. But switches, they do the exact opposite. They transmit on 3 and 6 and receive on 1 and 2. Back in the day, this was a massive headache. If you wanted to connect a PC straight to a router, you had to go track down a custom-wired crossover cable just to make sure the speaking pins lined up with the listening pins.
Thankfully, we don't have to worry about that anymore because modern networks feature Auto MDI-X. Honestly, it's the unsung hero of IT. It automatically senses what's plugged into the other end, and if it sees a collision coming, it literally swaps the transmit and receive pins digitally on the fly. It totally killed the crossover cable and made networking actual plug and play.
But what if you need to go further than 100 meters? That brings us to Section 3, sending data with light and breaking that distance barrier. To break past that copper wall, we ditch the electrical pulses and start using actual beams of light with fiber optics. And there are 2 main flavors here. First, multimode fiber. Think of it like shining a wide-beam flashlight down a mirrored hallway. It's cheaper, usually uses LEDs, but all that bouncing around limits how far it can go. Then you have single mode. This is entirely different. It's like firing a highly focused laser perfectly straight down a microscopic tube. Since it doesn't bounce, it can shoot data incredibly far.
And the difference in scale here is just absolutely staggering. While the 1000 base LX multimode standard maxes out around 550 meters, get this, the 10G base ER single mode standard can blast 10 gigabits of data up to a mind-blowing 30 kilometers. No boosters, no repeaters, just a straight shot of pure light carrying massive amounts of data across entire cities. It's just incredible.
Okay, wrapping things up with Section 4, the auto negotiation handshake, or how these devices actually agree to talk to each other.
So the next time you plug a cable in and hear that satisfying click, keep in mind that before you even touch your mouse, a super complex conversation has already kicked off.
Instantly, these two devices start what's called auto negotiation. Think of it like two diplomats meeting in a room to quickly establish the ground rules. They're figuring out the absolute highest speed and the best duplex setting they can both handle. The golden rule here, you generally just want to leave both ends set to auto so they can silently sort it out themselves.
And understanding that duplex setting is absolutely crucial. Half duplex is basically a narrow, one-way bridge. A device can send or receive, but only one stream at a time to avoid a crash. Full duplex? That's your modern two-way highway. You can send and receive at the exact same time. If there's a mismatch here, like one side thinks it's on a highway and the other thinks it's on a single-lane bridge, it literally tanks your network speed with constant digital collisions.
So if that negotiation fails and your internet speed is just crawling, remember this golden rule of IT. Always, always swap in a known good cable first. Before you start pulling your hair out over complex software settings, you have to rule out the physical wire. 9 times out of 10, a crushed cable or a bent pin is the actual culprit. It solves the mystery in seconds. It really is a massive, intricate system hidden right inside our walls, governed by these strict Ethernet standards. So, the next time you connect, ask yourself, is the physical layer right beneath your fingertips negotiating a simple one-way dirt road, or a blazing fast 30-kilometer fiber highway? Thanks for tuning into this explainer, and stay curious out there.